Alright everybody, welcome back to the second video on periodic trends. This is the one where I'm going to go through and I'm going to explain what the trends, why the trends are the way they are. This is really important, guys, because there's going to be a lot of questions on the AP test. They are definitely guarantee you're going to see something very similar to this or something along these lines. And students get this mixed up all the time. They give a hard time answering these questions. So please bookmark this video, watch this video a couple times just so that you can get down why the trends happen. Because I'm telling you, if you understand this, a lot of all the other chemistry stuff just kind of falls into place because it just kind of makes sense what's happening. All right. So if we think about periodic trends, let's take a look with we already know what they are. So I'm not going to go through with what the trends are at this point. What I'm going to do is I'm just going to explain how they come about. So what are we doing? First of all, in order to understand this, we have to have some common terminology that we're going to use. All right, so when we think about the atom, we've got to think about the fact that you've got a positive and a negative charge. And this is the forces that are counterbalanced inside the atom. You've got the pull of the nucleus on the electron. Or you could think of the electron's attraction to the proton. However you want to do it, there's some force of attraction between the proton and the electron. That's referred to as the effective nuclear charge. How strongly the nucleus can pull the electron. That's pretty much it, because if you think about it, if I have an ionization energy, it's the energy that I have to overcome this energy to get that electron to be ejected from the atom. So I need to know something about the ability for that nucleus to pull the electron. Okay. The other thing is that the electrons are in motion and they're trying to get away from the nucleus. You can kind of think because they have energy, so they're trying to continuously get away, but they're kind of pulled into the nucleus, and you get that angular momentum, and you get the electron to do something like moving or rotating around the nucleus. Okay. Now, something else that happens is there's something called electron shielding. Now, if the nucleus is trying to pull this electron, there could be a problem because there could be an earlier energy level. If I have energy level 1 in here, well, now I got electrons that are blocking it. This is the shielding effect. You get the shielding. So what that means is the effective nuclear charge, the ability for that nucleus to pull that electron, has been weakened. And every time I add a new energy level in there, I weaken the pull on that nucleus on that valence electron. So the question is, what energy level is this electron in? Because if it's an energy level 3, okay, then what it's doing is it's being shielded by these two energy levels, and that's electron shielding. Earlier energy levels that are filled will shield the outer electron. Now, shielding also comes up and takes part, it has a play in S and P's, because the S's are sublevels and the P's are sublevels. So within that second energy level, you have that S orbital, that S sublevel and that P sublevel that can actually have some shielding, and I'll show you that as we go along. Then the last one, which we don't use too often, there are a couple places. There's 3 places we're going to use the repulsion force, and that's when you have electrons in the same energy level. So if I put another electron here, these electrons are going to repel each other because they're now in the same energy level. They're now near each other. They're going to start pushing away. So when I put electrons in the same, remember, what's an orbital? An orbital is a region in space. So if I'm putting another electron in that same orbital, and that's what these things are representing, I'm putting electrons in the same spaces, so they're going to start repelling each other. Okay, so effective nuclear charge. Kind of already explained this. You can use, I tend to use this ZEFF. If you're going to use this on the AP test, make sure you define that this equals ZEFF. If you're going to use it, just makes it a little bit easier to write the answers out. You're not constantly typing effective nuclear charge. You're not constantly writing it. Okay, so the idea is that the higher the effective nuclear charge, the more it pulls on the electrons. I like to think about it as making the atom smaller, right? Because if the effective nuclear charge is getting stronger and stronger and stronger, it's going to pull those electrons more, making the atom effectively getting smaller and smaller and smaller. And as a result, ionization energy goes up, electronegativity goes up, electron affinity goes up as a result of all that. Okay? So we have to look at how these things are changing. How does effective nuclear charge change when I add shielding and repulsion? Because those two forces counteract the effective nuclear charge. So if I have shielding, that's going to reduce down the ability to pull. If I have electron repulsion, it's going to push electrons away, getting them to come further away from the nucleus. Okay? So we look at shielding, as I mentioned before. It happens when we add a new energy level. It's when the biggest dramatic shielding happens. You can have shielding, as I said, between an S and a P. Okay? So when we go down a family on the periodic table, that's where shielding becomes the greatest. So the effective nuclear charge is weaker and weaker as we go down a group or family, because that's when we add that new energy level. When we move across a period, this is important to know, across a period, shielding is pretty much constant, right? Because you're staying within that same energy level. Not completely constant because of that SP difference I'll talk about a little bit later, okay? But overall, from left to right, it tends to be constant. So if you want to put on your periodic table, you know what, don't do that. Forget it. I don't want you getting confused with that, because there's a lot of exceptions to that rule. Okay. All right. So let's take a look at electron or electron repulsion. Again, this is when we have electrons in the same orbital, same energy level. The electrons are going to start repelling each other. Here's the three places that only these three places, guys. You never, ever, ever will you mention electron repulsion in any other case. Okay, I'll talk about the P3 and the P4 formation of anions, and when we remove electrons from orbitals that already contain electrons, okay, from an orbital that contains other electrons, okay. So what that means is that, yes, you might think repulsion is going up, but if it's not one of these three cases that I will explain in a little bit, you're not going to see it, okay. You're not going to use this, okay. And it'll make more sense when we start looking at some examples. All right, so let's take a look at how effective nuclear charge works. Because if you can understand this part here, we're going to just take all the other trends and overlay them on this chart. Okay. If you notice, this looks a lot like the ionization energy chart, and it's not a mistake because I kind of fudged it. But it's okay because it works the same way. It really is going to follow the same pattern. So what am I talking about? What I'm looking at is I'm going to start with hydrogen. The hydrogen atom is here. And we're going to look at how its effective nuclear charge changes as I go from hydrogen to helium. Well, if I have hydrogen, it has that 1s, 1 electron. I go to helium, it has the 1s, 2 electron. So I stayed in the same energy level, so my shielding didn't change. Shielding pretty much stayed the same. You could argue, well, wait a minute, I have that 1s, and what I'm doing is I'm putting an electron in the same orbital. Isn't the electron repulsion going up? No! No, not here. True, it is, but because of the fact that I went from 1 proton, okay, over here, to 2 protons for this one, the increase in protons overrides this. Remember, there's only 3 places electron repulsion is going to have an effect, and this is not one of them. Okay, so don't get misled by that. Protons go up. Therefore, I have a higher effective nuclear charge. So it's from hydrogen to helium, effective nuclear charge dramatically goes up. And this is the game we're going to play. What's the consequence of that? Well, the atom gets smaller because the effective nuclear charge is larger, so it pulls the electrons more. And as a result, the electronegativity goes up. Ionization. The electron's going to be harder to remove now. This electron in the S2 is going to be really hard to move, the 1s2, the second electron, because of the fact that higher pull of the nucleus. Now look what happens when I go from helium to lithium. If I go to lithium, I now have a 1s2, 2s1. I've dramatically increased electron shielding, right? The electron shielding has gone up. I've added a new energy level. So I went from the first energy level, n equals 1, to n equals 2, and therefore I increase shielding. Remember I said shielding goes up when we have those earlier energy levels. So the n equals 2 has some shielding going on from the 1s. So we see a dramatic drop in effective nuclear charge. Okay, well, what does that mean? Well, if the effective nuclear charge has gone down dramatically, hey, that electron's going to be really easy to remove because it can't pull, the nucleus can't pull on that electron as strongly because it's being blocked by the first energy level. Do you see the game I'm playing here? You have to mention, when they explain, why does lithium have such a low ionization energy? It's because helium, and I say take that back, because lithium has shielding and the effective nuclear charge goes down due to that shielding because we've introduced a new energy level. So a new energy level has been added, shielding has gone up from the 1s energy level, and therefore this electron experiences a very low ionization energy. Now, if we remove that electron's gone because ionization energy was easy, real low, easy to remove it. Well, now we look at the next electron. Well, look what happens. That energy level is gone. We're now back into that first energy level. What happened to shielding? Well, shielding went down. So if shielding went down, what happened to the effective nuclear charge? Effective nuclear charge goes back up. So therefore, if I'm going to try to remove this electron, it's going to require a lot more energy because effective nuclear charge went up. Okay, that's how you're going to do it. You have to mention effective nuclear charge, you have to mention shielding, and at times you have to mention electron repulsion. All right, now a couple more anomalies we need to look at. If we go from lithium up to beryllium, okay, again, we're going to go for beryllium. We're going to have the B, E, we're going to have the 1s2, 2s2. Okay, same idea for helium as we did for, I'm sorry, from hydrogen to helium. Same answer for lithium to beryllium because we increased the electrons, but the protons went up, but we stayed in the same energy level. But look what happens when I go from beryllium to boron. When I go to boron, what happens is I go from 1s2, 2s2, 2p1. And we see a dramatic dip in the effective nuclear charge. Therefore, the effective nuclear charge is lower. What's going to happen to ionization energy? It's going to go down, right? Because you're not going to have as much energy to remove this electron. It's going to be a little bit easier to remove because we now increase, we added another electron, same energy level, shielding didn't go up, so therefore we're going to have, but here's the thing, we went from the S to the P, and that's where the shielding is going to come in. Even though we're in the same energy level, it has to do with the fact that the S's slightly shield the P's. And you don't have to know anything other than that. That would be fine for answering that question. Technically, it has something to refer to as the penetration effect of s orbitals closer to the nucleus than the p's. We don't need to really go there. What you just want to recognize is that an s orbital, an s sublevel will shield a p sublevel. Okay. All right, and then as you continue on, you go up to oxygen. Okay. Let me just check something real quick. Okay, I want to check that. I meant to say nitrogen. So this electron, or this atom right here would be nitrogen. So as we go from boron to nitrogen, we're just going to keep filling. We're going to do 2p2, 2p3, and then we go from nitrogen, which is, let's write nitrogen here, 1s2, 2s2, 2p3. What's happening is that orbital, we were staying in the same energy level, didn't change anything. We didn't add an S. There's no D added, so there's no other shielding going on. Essentially what's happening is we're staying in the same sublevel, we're staying in the same energy level, so therefore effective nuclear charge is going to go up and up and up. Now we go from nitrogen to oxygen. We're going from a P3 to a P4, and this happens all the way along this group. Anytime you're in this, the P3s to the P4s, whether it's 2 or 3P or 4P, we tend to see this more dramatically with the higher ones, with the smaller atoms, the atoms at the top of the periodic table. Notice the difference here, not much, and it kind of tapers off. We don't really need to worry about it. So really, we tend to see this more with the top portion of the periodic table. So what's going on? We're adding an electron, adding an electron, adding an electron. Okay, that's nitrogen. When we get to oxygen, what happens is we have to put another electron into the p orbital. So we're going to do that same orbital, okay, the same sublevel, the p. What we're going to do now is we're going to add another electron right here. And what happens here at this point by adding the extra electron is we have an increase in electron-electron repulsion. This is one of the few cases that electron-electron repulsion has an effect. So what's happening is because we're squeezing them, now think about this is an orbital, this is an orbital, this is an orbital. This is the sublevel, okay? So we're adding an electron into that particular sublevel, okay, into that particular orbital, which is the actual location of where the electron is. So they're closest here than they are here and here. Remember, electrons repel according to Hund's rule, and they go into different orbitals. Here they have to now stack up. So what we see is a dip in the effective nuclear charge because the repulsion force is pushing those electrons a little bit further away, and as a result, we see a little bit increase in atomic size, we see a little bit of decrease in ionization energy, and a decrease in electronegativity, and everything else that I've been saying over and over again. And then after that, we continue on because what we're going to do is add electrons into the P again and P again. Even though there is repulsion forces in here, it's all been already corrected for, and we're just kind of shifting over and then increasing again back to neon. And then the pattern starts over. Okay? And that's pretty much it. That is how we're going to explain this. Now I'm going to stop the video here because I think this is a pretty good place to stop. I'm going to do one more video. I know this is long, but I do want to do one more video just to kind of go through and actually use this idea of effective nuclear charge to go through each of the trends and explain them for you. But you should be able to go from this though, guys. And if you want to stop here and try answering some questions and take this information and apply it yourself, go for it and see what that does for you. All right, I'll see you guys in class.